Okay, today we're going to look at drawing some ray diagrams with concave and convex mirrors. So we're going to start with the 6 positions that you can put an image for a concave mirror. So we're going to note the object distance, which is DO, and the image distance, DI, at each position. So position 1, we're going to have an object that lies infinitely far from the mirror. So that would be like the sun out here, and all the rays that are coming in are going to be parallel to the principal axis. So I'm going to use my little ray diagram helper here. And again, parallel ray in, reflects, and goes through the focal point. And we'll do another one. So they converge at a point. So it says the image is real because they're converging rays, and it appears as a point of light in front of the mirror. So there's our figure. This should be an infinity symbol. My symbol font is not working on my printer, so all of the infinities are 8s. And then the image distance is at the focal point, so that distance is the same as the focal length, and it's real. Let's look at position 2. So now we're outside of C, but we're closer than infinity. So this should be infinity. So our distance is less than infinity, but greater than the radius, or the distance from C to V. So let's draw some rays. First one is parallel in, reflects through F, and then through F, reflects off parallel, and then you can do a third one, and this one is through C and back on itself. And if you notice, those 3 rays converge at the point right here. So again, you can see that it reflects through there, reflects on itself through that same point, reflects through that point. So this is where my image is located. And that is the top of my image, just like it came from the top of the object. Okay, so what do we notice about the image? Well, it's real, it's inverted, and has a magnification between -1 and 0. So an example of a number that's between -1 and 0 would be like -0.5. What does this mean? The negative means it's inverted, and the 0.5 means that it's half the size of the original, so it's smaller. So it's going to be inverted and smaller than the original object, and that's what we get. If you notice, the image will always be between C and F. Okay, so it's going to be in this area, and you'll see kind of as we creep this closer to C, this image comes closer to C. So it starts infinitely far away, it starts at F, the closer and closer we bring this, the closer and closer it brings it to C, which we're going to see next. So this one, the object is actually on C. So we have 2 rays that we can draw here. First one is parallel through F, and the other one is through F, and out parallel. And that should line up right at C. The third one, we don't have an option. We can't go through C and back on itself. There's no mirror up there. So we just draw 2. So the image here is again real. It's inverted. And now it's the same size. So what would the magnification be if it's the same size? It would be 1, but it's also inverted. So therefore it is -1. There's our third one. Let's go to our fourth. Now we're inside of C, but outside of F. So we're between C and F. Let's see what happens here. Again, parallel in, through F, through F, out parallel, and then you can't really do through C and back on itself on this one. So these two are fine. And if you notice, here's our image. So it is still real. It is still inverted. But this time, its magnification is bigger. So therefore, our magnification is going to be less than -1. Give me a number less than -1. How about -2? Remember, what's that tell us? The negative tells us it's inverted. 2 tells me it's twice as big as that. So this is now going to give me a bigger image than my object at this point. We're going to move to position 5, where we're on the focal point. In this case, we have no image formed, and we're going to see why that is. So if I draw, if it's a point, and it comes from F, then it leaves and reflects parallel. Will these converge? No. Do they appear to diverge? No. So you have no image produced. And we can do the same type of thing here. You do as if it's coming from C, and it reflects back on itself. And then we can do one that's in parallel, and then it reflects through F. And those are parallel lines, so they never converge as well. So we have no image produced. It says all light rays leave parallel to each other. And the application to this would be flashlight headlights, and so forth. That bulb is placed at the focal point so that all the rays are moving parallel to each other. Alright, let's go to our last position. This is kind of the only one that's different. Okay, this is the only one that's really different. So now the image is inside the focal point. So anyway, I'm going to do my same rays. I've got one that's parallel. And when it strikes, it's going to go through the focal point. And then I have another one as it's coming from F. So if you look here, I'm going to put my marker from F to the top. And as it's coming from F, it goes up here. And then when it strikes the mirror, it reflects how? Well, this case reflects off parallel. And now what are these two rays doing? They're diverging. So because they're diverging, they appear to diverge from a place. And that place is actually behind the mirror. So I'm going to draw this back into the mirror with little dotted lines. And I'm going to do the same thing. I'm going to take this reflected ray and draw it back into the mirror. So where do they appear to diverge from? They appear to come from this point right here and then spread out along the way. So now I'm going to draw my image. So what do we notice? This one now creates a virtual image. The image is upright. And it has a magnification now greater than 1. Now this example would be like a shaving mirror or a makeup mirror where you get inside the focal point with your face, and now you have a magnified image that looks like it's behind the mirror. Okay, so that's what a magnification mirror is. You're actually inside the focal point. But if you're outside the focal point, then everything's inverted, and it could be bigger or it could be smaller depending on where you are. So if you're looking at your spoon, we're looking at the inside of our spoon, so you can see that I'm inverted, but if I bring this closer, it actually flips right side up and is magnified at that point. So again, depending on what you're looking at and what the object is in the spoon, so I'm inverted there, and if I bring my finger closer, you can see it flips right side up and is now magnified inside. And eventually you can see my fingertip actually disappear in there. Okay? Those are concave mirrors. Let's look at convex. So we have some rays that we have. It says any incident light ray. So you have any incident light ray that is parallel to the principal axis reflected away from the focal point. And again, if you look at our diagram, the focal point and center of curvature are now behind this, because again, if this were a circle, our center of curvature would be here and our focal length is just halfway between. Here's my focal point, here's my center of curvature. Any incident light ray directed toward the focal point is reflected back parallel to the principal axis. Anything directed toward the center of curvature reflects back on itself. So let's look below. Let's draw these three. The first one, we have any incident ray that's parallel. So incident ray are the ones coming in. Reflects, and it reflects away from F. Alright, so this one is going to reflect away from F. So it's going to reflect this way. Okay, it hits the mirrored surface. Again, if we drew a line that was normal to the surface at that point, you can see it obeys the law of reflection still. But we're going to draw it back here with a dotted line, as if it came from F, and then reflects on. And then we're going to go one toward F, and when it strikes, it reflects off parallel. Again, law of reflection, we could put a normal line to that surface, and then again you can see that it's going to go off this way. So we're going to reflect it off parallel. And again, I'm drawing that reflected ray back into the surface of the mirror. And that's enough. 2 is enough. But I'm going to draw the third here just to show you that if I go through or towards C, it then reflects on itself. And if I draw that reflected ray back towards C, we can actually see that it came from this spot too. So if you notice, my reflected rays are all diverging, they're spreading out, and they appear to spread out from this point right here. So this is where I'm going to draw my image. And there's only 2 conditions for this. So if you notice, it says, so the rays do what? They diverge. So your eye thinks that they came and are diverging from this point. Okay? So let's look here. The image formed by a convex mirror will always be virtual. This is a result of diverging light rays, which appear behind the mirror. So it's virtual, it's always upright. Virtual images are always upright. And has a magnification between 0 and 1. So like 1/2, 0.5 is 1, so it's always going to be smaller and always upright. So let's look. If we have an object that's an infinite distance away, again, DO is infinity here, image appears as a point located at the focus. And we can see this. Parallel in reflects as if it came from F. So all these reflect as if they diverge and came from F. And then position 2, you can see our 3 rays, exactly what we just drew. So parallel in reflects as if it came from F. Toward F reflects as if it's parallel, and then toward C reflects on itself, and we get this guy right here. This is infinity.